Good day, viewers. I am creating these videos to help teachers of maths support their learners in making sense of mathematical concepts and their associated procedures and processes. And today I want to look at the one that first got me interested in working with manipulatives and visuals, and that is completing the square. I first saw this on episode 1 of the BBC show that Marcus de Soito did, a history of mathematics, and it was in relation to some area problem from ancient Egypt, and it literally blew me away that, oh, well, that's actually what completing the square looks like. So hopefully you'll enjoy this one as well, and if not, you can always go and find it's about halfway through that episode, about 30 minutes into that episode, so you can always go and find it and watch it on there. So I have my algebra tiles to help me, and we're going to make sense of what completing the square does and how it works using these. So we need to start with a quadratic expression, and so I'm going to start with a relatively simple quadratic expression to begin with: x squared plus 4x plus 7. And so I'm going to build that quadratic expression out of my tiles here. I've got x squared, I've got 4x's, and I've got 7 ones. And my instruction to pupils for this is simply build me a square. Build me a complete square, something that you know for sure is square. Okay, and you might get kids combining these in all sorts of fun and interesting ways, but eventually, if they are sort of used to quadratic expanding and quadratic factorizing with these sort of tiles, then what you'll eventually end up with is potentially something that looks like this to begin with. So you'll have an x squared, and then you'll have the 2x's here and the 2x's there. Occasionally, you see that particularly with 4x, with x's around each side, but typically, particularly like say if they've used them before for expanding and factorizing, then they're used to having a blue square at the top left, x's on either side of it. And then, of course, what they'll do is they'll fit their 1 tiles in, and what we can see here is we've got a complete x square, or a complete square, sorry, with 3 extra ones. And then we could talk about, okay, so what is the length, or what is the dimension of your complete square? And we can see that this is x plus 2 long by x plus 2 wide. And so what we've got here is we have a complete x plus 2 square plus an extra 3 that we haven't managed to fit into our square. And what's nice about this, what's particularly nice about this, I particularly like, is we can start to make sense of why this coefficient of x, in this case 4, is always going to be halved. Because in order to actually build a complete square, you're going to have half of them vertically attached to the sides of the square, either both on the same side or maybe one on one side, one on the other. And you're going to have half your x's horizontal attached to the base, or maybe to the horizontal side, either horizontal side of the square. And so we can start to see why that coefficient of x is always going to be halved in that sort of case. And then I might move on to something involving negatives. So I might move on to something, say, -1. And so rather than having these 7 ones, which I'm just going to pull out of the way for now, we've got this -1. Now, of course, because of the fact that 1s and -1s actually have the same physical area, pupils are sometimes tempted to put that in there. But what they've got to be clear on here, and again, it helps if they've worked with expanding and factorizing with these things, is that if this is going to be x, then this is 1 times x. So this has got to be +1. And similarly, this is 1 times x. So this would only be fillable with a +1. So what I have here is this -1 that I can't put into this space. Now, there's a couple of different ways we might interpret that. And we might interpret that as, well, I have got 4 less than my complete square and an extra -1. So that might be, I have an x plus 2 square, but I have 4 less than that because I haven't managed to fill the space of 4, plus an extra -1. And if in particular, your procedure for completing the square tends to be sort of concentrate on the first two terms of the expression, the x squared and the x, get those to sort out the brackets, then minus whatever square you get from squaring the number, and then add or subtract however many sort of coefficient you have left from or constant term, sorry, that you have left from the end of your original quadratic, then this might suit you. Or alternatively, what we might do, and obviously then we would write that as -5, we'd write this bit as -5. Alternatively, what we might do there is we might say, right, well, in order to actually physically complete this square, I am going to need 4 1 tiles. But I can't just introduce 4 1 tiles because now I've changed the expression. It's no longer x squared plus 4x minus 1. It's now x squared plus 4x, technically plus 3. But what I could do is, rather than remove these 1 tiles again, is I could put in 4 -1 tiles. And now that expression is x squared plus 4x minus 1. Of course, this relies on pupils having seen and being familiar with the idea of zero pairs, that if I introduce a 1, I can introduce a -1 to balance it because the result is 0. And so now I can see actually that what I have is a complete x square. But to complete that x square, I had to introduce 4 1 tiles. So I've had to introduce 4 -1 tiles, and there's our -4 again. And of course, I have my -1 from before, which altogether makes -5. And that's, either way works, even when sort of your constant term in your original quadratic, your expanded quadratic, is positive, but the result of the sort of constant term in the complete the square form would be negative. So say, for example, we looked at just very quickly x squared plus 4x plus 3. So I don't need any of these -1s for now. And I've got my 3. So you can see here I've got my x squared plus 4x plus 3, and I've been through the process of trying to arrange those as a square. Well, I can see that in this case, again, I've got nearly a complete x plus 2 square. But what I have is 1 less than a completed x plus 2 square. So I could just put a -1 straight in there because I have 1 less. Or I could say, well, to complete that square, I have to add an extra 1. So that means I'm going to have to -1. And so again, we can see that what I have is a completed x plus 2 square with a -1. And so that will work equally well, even though there's nothing negative here, to introduce the negatives there. What about then if we have a quadratic that doesn't have a coefficient of x squared as 1? Maybe something like 2x squared plus 4x plus 3. Well, if I build that expression, here's my 2x squared, here's my 4x, and here's my 3. Then what we can see is that in reality, there's sort of no way that I'm going to be able to get anywhere near a complete square by fitting those together. I mean, this looks like it might be close to a square, but we know it's not. We know that this is not equal in length to that. And even though it looks like it's close, that's only because the value of x does have to take on a fixed value when we're using these tiles. We can't vary a bit. But if this, if x was quite large, this length could potentially be way, way bigger than 4 1s. So that's not going to help us here. So what we can do instead here, and this is where I'd modify my instruction to say, right, well, actually, what I'd like to do, rather than build me a single complete square, is to build me 2 complete squares, each one or as close as you can to 2 complete squares, each one based on a single of the x squared. And of course, that is me taking out that factor of 2. And so what I'm going to see now is, okay, well, I'm going to need sort of to split my x's equally. And technically, I could do this, because there isn't really a need to split my 1's equally there. I mean, I could split my 1's equally. You can't do it if you've got the physical tiles unless they're made of paper and you can cut them in half. I can split this 1 equally using the split options on MathSpot, and I could sort of put 1.5 of the 1's there and 1.5 of the 1's there and then show that a 1 fits into each gap. But actually, I don't really need to for this. I could just leave my 3 separately and say, right, okay, well, what's going to happen now is I'm going to put 1 of my 1's in there and 1 of my 1's in here. So what I have now is I have 2 complete x plus 1 squares, and I have an extra 1 tile. And of course, if I'd have split this one in half, I'd have had an extra half here and the extra half here, and that would have said I'd have had 2. I'll write it in here, I'd have had 2 sort of big bracket x plus 1 squareds plus a half, because I've had a half of this one here and a half of this one here. But then I would have just multiplied that 2 by a half to get me back to that anyway. So even if I had wrapped the factor of 2 around the 3 as well and made that 1.5, it wouldn't have made any difference to the eventual expression. And I see some people do that, but actually, it's not really necessary. The focus on the 2 is on this bit, and then I can pull the 1's in for different places as I need to. Okay, so that is my sort of short video on completing the square and how you might help learners make sense of what's going on with completing the square, both using manipulatives and visuals, and sort of working through things like why the coefficient of x is going to be halved and stuff like that. As always, I'd like to say a big thank you to mathspot.com and its creator, Jonathan Hall, for the wonderful website that houses all of these virtual manipulatives, but as you can see along the bottom here, houses so many more things. The manipulatives is what I've been using, but there's a huge amount of resource in the GCSEs, question generators, starters, tools, all sorts of lovely things in there. So if you've never been to mathspot.com before, I can heartily recommend you give it a good look through. It will help you in your teaching. I can pretty much guarantee that. And as always, if you're interested in use of visuals and manipulatives to support pupils in making sense of mathematical concepts, then I would ask you to check out my website, visiblemaths.co.uk, where amongst many things on there, you will find a link to my book, which is also titled Visible Maths. And on the link there is a link to the publisher, which is Crown House Publishing. And on their website, you can view some sample pages. And if you feel like it will be useful, you can place an order. I am aiming to make these videos throughout lockdown and potentially even beyond. So if there is a particular maths concept or procedure or process that you feel like you would want to see modeled using manipulatives and visuals, then please do get in touch and hopefully I'll be able to get around to making it for you. Thank you very much for your kind attention.